get started here. So we're very happy today to have Bernard Carr visiting us from Queen Mary University of London. Bernard got his PhD at Cambridge under Stephen Hawking. Traveled the world for a while, interacting at various places before returning to Cambridge for a few years, and then finally taking a position at Queen Mary, where he's been ever since. Bernard is a pioneer in many things, most especially Hawking on the early theory of primordial black holes and continuing to develop that until today. Also, I believe his is the first recorded use of the word anthropic principle, and one of the pioneers of the weak anthropic principle.
Strong as well. Yeah.
Strong as well. Amongst a large amount of work over a whole range of topics in cosmology, general relativity, and quantum mechanics. So we're very happy to have him here to talk about primordial black holes.
Thank you. Yeah. Well, it's true I've worked on many things, but that merely reflects the fact that I'm rather old. Anyway, it's a great delight to come back here. In the early days of CITA, I was quite a regular visitor, but I haven't been back, I think, for 4 years. So it's great to be here. And I'm going to talk about primordial black holes because they're rather topical at the moment. And I'm going to ask whether they can provide the dark matter. I've spent something like 40 years of my life working on these things, so it would be quite nice if they did do something useful. Now, the plan of my talk, I'm going to start off giving a rather general introduction about black holes and dark matter to put this in a broader context. But then I'm going to focus more specifically on primordial black holes, how they form, and what sort of constraints we have on them. I should say at the outset, we don't know that primordial black holes exist at all, even though I've worked on them for 40 years. But we live in hope. And I'm going to argue that there are 3 special mass windows in which primordial black holes could in fact provide the dark mass. And I'm going to talk about the prospects of that. Now, I should say that this, most of this talk is related to, well, the second part of the talk is related to a paper which has recently come out with Florian Kuhnel and Marit Sandstedt. Now, when I was having dinner last night, the person sitting opposite me read this abstract and he made a most profound remark. He said that the last sentence, the possibility of Planck relics is intriguing but virtually untestable, he said that will stop anybody coming to the seminar if it's untestable. And indeed, maybe that's true. And then I thought, well, maybe it will also stop anybody reading the paper. So what I now need to do, I need to hide that. It's intriguing. Is that what you call redacting or something, I think? But anyway. Now, let me just remind you about black holes. You all know, of course, black holes, mass m, have got a certain radius and a corresponding density, which goes like mass to the -2. And of course, we've got very good evidence for the stellar black holes, 1 to 100 solar masses, possibly intermediate mass black holes, which are ones in the range of 1,000 to 100,000 solar masses, and definitely for supermassive black holes, which are anywhere between 1 million and 1 billion. And just to remind you, here's some evidence of Cygnus X1. In 2010, they actually observed a collapse to a black hole. And of course, most recently, we've had the LIGO direct detection of a black hole binary. The evidence for intermediate mass black holes is more ambiguous, but it's been suggested they are related to ultraluminous X-ray sources. Some might exist in globular clusters, and some people think they might be related to gamma ray bursts. And supermassive black holes, well, of course, we know there's 4 million solar mass one in our galaxy. Typical quasars are powered by 10 to the 8 solar masses, and they go all the way up. I think the record now is actually 12 billion solar masses. So these things are really enormous. But of course, none of these sorts of black holes can explain the dark matter problem. The density is much too low for that. This is just to remind you of the first exciting detection of binary black holes, and to also, of course, remind you that the important thing about this was that the masses of the black holes were of order 30 solar masses, and the final one was of order 60 solar masses, which is almost into the intermediate mass range. But now I want to talk about primordial black holes, so I'll just remind you of that formula. And what you notice from that formula is that if you want to make a small black hole, the density has to be very large. And that's why we don't think we can ever form black holes smaller than about a solar mass at the present epoch. However, black holes can form in the early universe because the density of the universe in the Big Bang picture just goes like 1 over t squared. And if you can compare that density with that mass, you immediately see that a black hole which is going to form at time t would have essentially something of order the horizon mass. And that goes all the way from, say, 10 to the minus 5 grams, the Planck mass, if it formed at the Planck time, 10 to the 15 grams, about the mass of a mountain, if it formed at 10 to the minus 23 seconds. And if it formed at 1 second, which might be a sort of reasonable maximum, it would be something like 10 to the 5th solar masses. So the point is that primordial black holes can span a huge range of masses, and that's what makes them interesting. How do they form? I mean, I've argued that in principle they can form because the density of the early universe can be arbitrarily high, but you still got to have some mechanism, because if the universe was exactly smooth, you'd never form any black holes. Now, the most obvious way in which they would form would be from inhomogeneities, such as would be generated by inflation. Of course, we know there are inhomogeneities because we're here, and we have to make galaxies, but we need somewhat bigger inhomogeneities to make primordial black holes, as we'll see. Another possibility is that the pressure, there might have been a phase transition in the early universe which reduced the pressure, and that means it's much more easy to form a black hole. This is the density perturbation required to form a black hole, and it sort of goes down if you go through a phase transition where the pressure is reduced, and that can happen. You still need it to be spherically symmetric, but that can happen. Cosmic strings, if people aren't so interested in cosmic strings now, but in principle we know cosmic strings can form, they can self-intersect and form loops, and under certain circumstances those loops can shrink and form black holes. Basically, if the loops get sufficiently condensed, they'll collapse to a black hole. The probability of that depends upon the mu parameter, and in fact we know already from the fact we mustn't make too many black holes that g mu must be less than 10 to the minus 6. Which is in itself quite an interesting constraint. People don't think strings really make large-scale structure anyway, but this in itself is an interesting limit. And the other possibility is that you can have a phase transition, a symmetry-breaking epoch, which produces bubbles of broken symmetry, and then the bubbles can collide, and under certain circumstances, the collisions of bubbles are going to make these primordial black holes. It needs fine-tuning, because if the bubbles collide too rapidly, you just make a smooth universe. If they don't collide rapidly enough, then you just get big inhomogeneities. So, but at least in principle, it can happen. But then, of course, the really interesting thing about primordial black holes is that because they can be small, quantum effects can be important. Oh, I can use this. And you know there's the famous Hawking temperature, which goes like 1 over the mass. And that means that the black hole evaporates on a timescale which goes like m cubed. For the sun, this is enormously long. It's about a millionth of a degree. But if you had a black hole of 10 to the 15 grams, which is the mass of a mountain but the size of a proton, then these would have a lifetime of the age of the universe, so they would actually be exploding today. And we knew very early, I mean, I was lucky to be doing my PhD with Stephen in 1974, and one knew immediately there couldn't be many of these things because most of their life these black holes are sizzling away and producing gamma rays. And the gamma ray background density at 100 MeV already tells us that the density parameter of the black holes in units of the critical density with this mass range has to be less than 10 to the minus 8. So we already knew right at the beginning that was a rather low probability of detecting the black hole explosions. This is what we really, what Stephen really wanted, because then he would get his Nobel Prize. But there's still no evidence for black hole explosions, although some people, David Klein, the late David Klein, has argued that actually there's a subset of gamma ray bursts which could be exploding black holes. But of course, from the point of view of today's seminar, the important point is that the black holes have to be bigger than 10 to the 15 grams if they're going to make the dark matter. So I'm not going to talk much about evaporating black holes today. It's quite interesting. You can ask, what is the mass of a black hole such that the temperature exceeds the microwave background? And it's basically the mass of the Earth. It's about 10 to the 26 grams. And I refer to I define a quantum black hole to be a black hole whose temperature is less than the microwave background. And it's basically the mass of the Earth, and it's about a centimeter. Well, as you know, what was really so exciting about all of this discovery, it was a great breakthrough in physics because it combined quantum mechanics, general relativity, and thermodynamics. And so really, even if primordial black holes don't exist, it's been incredibly important to think about them, because it was only when Stephen realized they could exist that he started thinking about the quantum effects of small black holes. Yes? Well, oh, sorry, Heisenberg and Boltzmann. Thank you. Yeah, I should have said that. And that's Einstein. Yeah. Now, I have to plug my own book here. I'm not putting it in the same category. I wrote a book on quantum black holes with my co-authors, Xavier Carr and Elizabeth Winstanley. The arrow's going in this direction to imply that it's not important in the same way that these things were, anyway, so the whole domain of quantum black holes is, of course, is a huge field of excitement ever since '74, and even now, 40 years later, they're still trying to figure out, you know, how we solve the information paradox. We even had a nice talk about it 2 days ago. Oh, he's not here. Anyway, now, why are primordial black holes important? The ones less than 10 to the 15 grams are a unique probe of the early universe. See, they probe in homogeneities, phase transitions, and inflation. The ones which are about 10 to the 15 grams, they're exploding today, and if we manage to see one exploding, they are a unique probe of high energy physics. They could generate cosmic rays and gamma ray background and things. The ones which are bigger than 10 to the 15 grams, quantum effects aren't important, but of course their gravity is important, and in particular, as I'm going to stress in this talk, they could make dark matter. They could also have some link with dark energy and dark dimensions. And the ones of about the Planck mass, they would be a probe of quantum gravity. And actually, these are the ones which most interest me at the moment. And they could be the Planck mass relics, which could also, in principle, be the dark mass. And it relates to things like generalized uncertainty principle and theories of quantum gravity. But I won't get into that in too much detail. I just want to give you some idea about, you know, the wide range of physics which is touched on.
Those 10 to the minus 5 grams, they all are done by now, aren't they?
Well, they would in principle, yes. But the point is that they would evaporate on the Planck timescale. But no one really knows what happens when a mass gets back to 10 to the minus 10 to the minus 5 grams, because the standard derivation breaks down. And a lot of people have suggested that maybe the black hole evaporation stops when you get to the Planck mass for various reasons. So that these Planck mass black holes could be relics. And as I said, even if they don't exist, they're really important. And I think that's an important message, because people sometimes get too obsessed with whether something's true or not. I mean, it can be useful to think about something in physics, even if it turns out.
How do they stop it from evaporating?
Well, they're different sorts of. There are all sorts of different scenarios, really. I have a scenario which relates to the generalized uncertainty principle. You might be related to string effects. I mean, there's no one scenario, but I mean, the basic argument is that we just don't know what happens when we get down to the Planck mass. So there may be 3 or 4 schemes, specific schemes, for making them stopping evaporating, as I said, including the generalized uncertainty principle. But the main point is we just don't know for sure what happens at that point. But these are odd things. They're the Planck scale. They're the smallest things you could ever have in the universe. That's why in my introduction, you remember my little abstract referred to something being virtually undetectable. Well, that's why it's the Planck scale. Anyway, so the other thing in these introductory remarks I want to stress is that, and in a way this relates to Dick's question, When you get down to very small scales, the world could have higher dimensions. We know in M theory they compactified higher dimensions. Normally, those dimensions are compactified on the Planck scale. That's the sort of Calabi-Yau space, and so nothing interesting happens. But in some of the scenarios, the dimensions can be much larger than the Planck scale. And so this volume, the volume of the compactified dimensions, can be much larger than the normal Planck volume. And then you have an effective quantum gravity mass scale, which is much less than the normal Planck mass, which is 10 to the 19 GeV. And this gives rise to the possibility of TeV quantum gravity, the idea that you might be able to detect black holes in the Large Hadron Collider. But in fact, it can happen in other contexts. I mean, it would be relevant to the early universe. It would be relevant to cosmic rays as well as the Large Hadron Collider. And the basic point is that if you've got these extra dimensions, once you go below the scale on which they're compactified, gravity goes up faster than 1 over r squared. So in some sense, it's easier to make black holes. And the radius of the black hole depends on its dependence on the mass, depends on the number of extra dimensions, the temperature depends on it. So everything changes from the standard result, but at least in a way that is well understood. And so it would be very exciting because in principle you would be able to detect these things at the Large Hadron Collider and probe the extra dimensions. Well, I don't want to go into the details of this except to say that there is at the moment no evidence from the LHC for this. I won't go through this. Now, so I just want to finish this sort of introductory part of this talk by putting this all into a big picture for you. Because this is my favorite picture. It's the cosmic Ouroboros, which is the snake swallowing its own tail. And as you go around the body of the snake, you go all the way up from the Planck scale, all the way up to the scale of the observable universe. And around the edges, you have all the things which people at the bottom, mountains, planets, stars, galaxies. And at the smaller scales, you've got ants, amoebas, DNA, atoms, subatomic particles. So the snake is like a ruler which encompasses all the scales of physical reality. But the only reason I'm showing it now is because I want to show you where black holes fit into this. Because all these black holes I've talked about, we can analyze them by their size, and I can put them around the body of this snake. And I'll do it in this historical order. So there are the stellar black holes, about 1 kilometer in size. There's the black hole in the middle of the Milky Way, the black holes powering quasars, the black holes evaporating. I'm going forward in time now. The black holes exploding today, the intermediate mass black holes, lunar mass. Now, the primordial black holes are here. And so lunar black holes are going to turn out to be possible dark matter candidates, terrestrial mass black holes, and then Planck mass black holes. And in some sense, the whole universe is a black hole, but I won't get into that. So the point is, most people who think about black holes normally focus on one particular mass range. But really, I mean, I guess I've devoted most of my life to thinking of black holes, and you really have to think of them over this huge range of scales. And now there at the bottom, of course, you've got the quantum classical divide, and there at the top, you've got the possibility of higher dimensions. Well, that's my general introduction, really. But let me just, and then if you want to think the dark matter is something to do with black holes, essentially it's Planck mass relics, lunar or intermediate mass black holes, as we'll see. And then, of course, you can, this is just a sort of historical diagram showing when the black holes form relative to the history of the universe. Obviously, primordial black holes form at early times, then supermassive, intermediate, stellar black holes. And then the accelerating black holes. And, but I do have to stress that there isn't actually any evidence for the accelerating black holes or primordial black holes. And then here is just a brief summary of all the quantum.
So I missed
accelerating
black holes. What exactly are accelerating black holes?
Sorry, I mean the ones made in the Large Hadron Collider.
Oh.
That's made in accelerate. Exactly. Dick's always very good on the actual meaning words, accelerator, not accelerating black holes. Thank you. Now, so it's quite interesting to get an overview of the various quantum and astrophysical effects of black holes. So here I've got the mass range. These are microscopic and macroscopic, scale of a micron. Just to give an overview, there are the quantum effects, which are small mass effects, lensing effects. You'll see why these particular mass ranges are important. These are the accretion effects, gravitational radiation effects, including LIGO, dynamical effects, and the possible dark matter candidates, again anticipating what I'm going to say later. So this diagram, you're looking at a bit puzzled though.
I'm wondering what sets the upper edge of the quantum?
The upper, the upper limit is the one at which they evaporate by the present epoch. You're right, because earlier on I took the upper limit to be 10 to the 26 grams, but here I'm just regarding 10 to the 26 grams are in principle quantum objects, but you don't in practice measure quantum effects.
Your scales, it's really close by.
Well, there's quite a big difference between 15 and 26, actually, yeah. Now I want to get on to the business of dark matter. Now, this will be all well known to all of you. As you know, we know the baryonic density parameter from Big Bang nucleosynthesis is about 5%. And of course, that's confirmed by the CMB and galaxy surveys and baryon-acoustic oscillations. And we know the visible density is something like 0.01 and the dark matter density is something like 0.3. These aren't the most precise figures, but that's what I could remember for the talk. But of course, the key point of that is that you need both baryonic and non-baryonic dark matter. You need baryonic dark matter because that is less than that, and you need non-baryonic dark matter because that is less than that. And so this has always given rise to the idea that you may have machos or WIMPs. In some sense, primordial black holes are both machos and WIMPs. They're non-baryonic, but in some sense they're like WIMPs. They're like WIMPs in terms of their scale, and they're dynamically like WIMPs, but they're like machos because they've got high mass and they have some of the sort of astrophysical consequences. And because Dick's in the audience, before I get into the primordial black holes, I want to say a little bit about the non-primordial population 3 black holes, because this was a topic which I worked on with Dick for many years, and I think it's of historic interest. So the question was, could the dark mass be in the black hole remnants of very massive stars, what we call population 3, not primordial, population 3 stars. And in the 80s, we did a lot of work on that, and we were able to sort of, for example, constrain in this paper. This is the density versus the mass, and we looked at the output of light and the metal enrichment and remnants and things like that. And we found the most likely range for the machos was the so-called VMO mass range, very massive object mass range. Now, so that's what we focused on. When we worked on this, nobody believed in VMOs. It was thought they were unstable. Nowadays, it's taken for granted that the first stars may have been VMOs, but people don't think they make up the dark mass. But nowadays, they're called intermediate mass black holes. So I'll normally use the phrase intermediate black holes, but they are essentially in the same range as VMO black holes. Now, one of the interesting aspects of this was that we realized that they would produce a lot of infrared background, especially if there was dust, because the precursors of the black holes, they produce a lot of light, and that gets redshifted into the infrared, or it even gets reprocessed by dust into the far infrared. And I was saying last night how there was a time when there was an announcement they'd found the infrared background, the Nagoya-Berkeley experiment. So we were very excited because we thought this confirmed the picture. And sadly, that turned out to be a false alarm. It wasn't a real background, but nevertheless, it did. With Craig Hogan, it did prompt us to study the effects of some of these backgrounds, which was actually, I think, rather useful later on. Now, the other thing I can't resist stressing is the importance of the gravitational waves, because we appreciated that this is a paper with Dick in '84. We realized that if there were these black holes, they would be in binaries, and there should be a population of black holes, binary black holes. Well, the black holes themselves would generate a gravitational wave background with a well-defined period and amplitude, but we also were interested in the fact there would be binary black holes which would coalesce and be detectable by various methods. And we were interested in which regime of mass and redshift we would be able to detect these objects, either the collapse of the black holes or the coalescences. And I'm just really blowing my own trumpet now, because of course now, 30 years later, they've discovered binary black holes, not necessarily in the VMO range, but pretty close to that. And everyone's forgotten this paper because it was done so long ago. But nevertheless, I found it very exciting that it was. And if they do find any intermediate mass black holes, which is only a little bit bigger than 60, it'll be well. Most things I work on turn out not to exist, so it's really quite nice if occasionally. Yeah. And there, of course, is the. Well, now there are two of these candidates. But the interesting thing is, could the LIGO black holes actually be related to the dark matter? Could they actually be? I mean, they have a mass of 10 or more solar masses. Could they actually be related to the dark mass? Or could they actually be primordial? Could they be primordial black holes? And that's one of the issues I want to address. If so, it's rather ironic, because although we were very interested in the possibility that the intermediate mass black holes provided the dark mass, that will turn out to have been correct, except they were the black holes coming from the primordial origin, not from these population 3 stars. Now, a lot of people in the wake of the LIGO detection have talked about this. There's a paper by Bird, Did LIGO Detect Dark Matter? They were arguing that black holes in the range 20 to 100 solar masses could well provide the inferred coalescence rate from LIGO. And then people have asked specifically whether they could be primordial black holes, because actually the fact that you've got a binary black hole doesn't really tell you whether it's primordial or not, because of course the time scale on which they're coalescing is much longer than the time scale on which they formed. But of course, if they are related to the dark mass, we will see they would have to be primordial. I mean, basically they would have to be primordial if they're producing the dark mass because of the nucleosynthesis constraints.
But the binary is not primordial, right? It's the binary somehow forms.
The binary, yes. The most natural picture is that the binary would form later. That's the big difference between the binaries forming at late times and early times. A primordial black hole will almost certainly be formed singly and capture later, whereas the stars, massive stars, would probably form in binaries. So that's one of the important issues. But you can't tell from the coalescences directly whether they were actually primordial or sort of late epoch. But there are all sorts of people have looked at the question how you can tell the difference. Eroshenko has argued that the tidal forces associated with inflationary perturbation will suppress the merger rate and makes it rather unlikely primordial black holes could provide the dark mass. There's a paper by Sasaki et al. Coming to much the same conclusions. In other words, they're saying it's unlikely that they could have the critical density. Koszlinski has got a paper arguing that the sources of these gravitational waves could be primordial and could also furthermore explain an infrared background by a rather indirect argument, which I won't go into. So there's a huge amount of interest in this. And I think the way to put it is that there's no need to invoke primordial black holes to explain the LIGO events. But they could in principle, because after all, I think I'm right in saying no one really expected the first black holes to be as large. as they were. Now, let's go back to primordial black holes then. I told you how they form, the different scenarios, but one of the questions is, what fraction of the universe went into primordial black holes? And it's easy to see that the fraction of the universe that went into primordial black holes must have been tiny. And it's a very simple argument. You take the density of the black holes to the microwave background. Today, this is the density parameter. It's this ratio, omega over 10 to the minus 4. As you go back into early times, the radiation density goes up faster than the matter density. So this ratio actually becomes smaller. This is the scale factor. And so it's very easy to see that the fraction of the universe going into black holes at the formation time is just related to T, the time. This should really be an equality, actually. It's just related to T. But T is related to M, so you have an immediate constraint on beta as a function of M. And that's basically saying only a tiny fraction of the early universe can have gone into primordial black holes. Now, this limit can be used in various ways. For the unevaporated ones, we simply have to say their density has to be less than 0.25. That's the cold dark matter density. If they're evaporating now, we've got the constraints saying that the gamma ray background says omega pBh on that mass scale must be less than 10 to the minus 8. If they evaporated in the past, there must be all sorts of constraints associated with entry production, Big Bang nucleosynthesis. These were the limits way back in 94. So this is beta as a function of M, and these are the regions which are excluded. This is the density, this is the gamma ray, this is nucleosynthesis, these are the dark matter relics. These have been updated. Many people produce these diagrams, but I'm afraid, focusing on my own. This was a paper we did with the Japanese in 2010, basically showing all the constraints on beta as a function of mass from zillions of effects. I think I talked about this at my last CITA seminar, and it took too long. But anyway, here's beta as a function of M. The important thing you've got to get from this diagram is that over a huge range of masses, from 10 to the 9th to 10 to the 17 grams, the fraction of the universe going into these primordial black holes is absolutely tiny. The galactic background says it's less than 10 to the minus 26. And I won't go into where these constraints come from, but they're to do with nucleosynthesis, gamma ray background, extragalactic cosmic rays, neutrinos, LSP particles, CMB distortions, etc. So the main message is that the fraction of the universe going into primordial black holes over that mass range is absolutely tiny. But it only needs to be tiny to produce the dark mass. Now, let me say a little bit more about how primordial black holes form. This was the first work I ever did. It's 40 years ago, which is a bit terrifying to think. But anyway, let's imagine we've got inhomogeneises. Then, in order you have an overdense region stops expanding, it's got to collapse against the pressure. It's easy to show when it does that, it's got to be bigger than the Jeans length, which is basically the square root of CT, where P equals alpha rho is the equation of state. And so that's when it stops expanding. And it's easy to show that this means that delta H, that is the amplitude of the fluctuation when it comes inside the horizon, that's got to be bigger than alpha. Now, most likely you have Gaussian fluctuations with some value epsilon, which will generally be very small. And so generally speaking, you're looking at, this is your Gaussian distribution, it's got a variance which is epsilon, and you're looking at the tail of the fluctuations, the high Gaussian tail. And therefore it's easy to see that the fraction of the universe collapsing just depends exponentially on the value of epsilon. It depends upon alpha, because of the equation of state, but it depends exponentially on 1 over epsilon squared. And so the point is, although it's true that we know only a small fraction of the universe can go into primordial black holes, it's also expected because of this exponential sensitivity. And if, for example, if epsilon was constant, then beta would also be constant, and you could predict the mass function uniquely. I'm going to just get rid of a few of these. So let's just see how you interpret this. If you then plot, if you've got beta as a function of epsilon, the constraints on beta, which I showed you before, will give constraints on epsilon. The epsilon, remember, is the expected fluctuation amplitude as a function of mass. And so again, these are the regions which are excluded. Now, of course, we know down from large-scale structure and Kobe, etc., the amplitude of the fluctuations on this scale is very, very small. It's 10 to the minus 5. So what this is showing is that if you want to make primordial black holes, you have to have a spectrum which is, so large-scale structure is only looking at that narrow range of scales there. So the important qualitative point at the primordial black holes are a unique probe of the value of epsilon on very, very small scales. And it's also clear that you could actually only make them if your spectrum was blue, in the sense that it got bigger with decreasing scale or had some special feature. So that's the first point to make, that it's putting strong constraints on the spectrum of fluctuations. But actually, you can look at this analysis a little bit more precisely. And the argument I gave basically says that delta has to be bigger than 0.3. That was roughly confirmed by numerical studies. But later on, it was found that the formation of a primordial black hole is really an example of what's called critical phenomena, the phenomena of critical collapse. And this was a most important discovery which goes back to Chopwick originally, which says that if you take delta, you have to be above some threshold, delta C, in order to make a primordial black hole. But you find that as delta goes towards delta C, the mass of the black hole scales as delta minus delta C to some power gamma. So the mass actually goes to 0. And that's a symptom of what's called critical collapse, that you get black holes of arbitrarily small mass. And this happens in the context of forming primordial black holes. And that's quite important, because the original picture just said that you form black holes at the horizon mass, essentially. This is saying you also form black holes with a much more extended spectrum, going down to much lower masses. And this is most certainly the correct way to look at this. And then lots of people did more careful calculations to find out what this critical value of delta was. And it turns out to be something like 0.4, which is a little bit bigger than 0.3. That comes from detailed numerical calculations. But what that means is that this is the mass relationship between the mass and the delta minus delta C. But what it means is the spectrum, the mass function of the black holes, instead of being peaked at the horizon mass, actually has a tail, a low mass tail. And that's going to turn out to be quite important when we come on to look at the dark matter problem. And in fact, you can even predict very precisely what that mass function is. So this is a sort of a fairly precise prediction as to what the form of the PBH mass function is likely to be. Now, how do the primordial black holes form? They would most naturally form through inflation. I'm going to cut out the part of my talk on inflation because you can ask me about it later. But let me just say that an obvious source of the fluctuations which will be making the primordial black holes is inflation. And on a sufficiently small scale, I'll show this on a sufficiently small scale, inflation just actually dilutes the black holes, it inflates them away, but it generates the fluctuations which later make the black holes themselves. And let me just say, I mean, there's a huge literature on this. Any scenario you can give me for inflation, you can calculate how many primordial black holes will form, and that puts constraints on the inflationary scenario. But I won't go into any more details about that. I now want to get on to the question. Well, let me just say this. We're interested in the question of whether the dark mass can be intermediate mass black holes. So let me just say that there's been a lot of interest recently in the possibility that inflation is going to generate primordial black holes in the intermediate mass range. And I'll just show some of these references. I mean, the idea is that you actually need a secondary inflation phase, but there was this paper in 2010. Since then, there have been a lot of papers, I've not shown all of them, all basically arguing that if you invoke, well, what was often called the waterfall or hybrid inflation, that you naturally can get primordial black holes in the intermediate mass range. Now, bear in mind, those are the ones which we're going to be interested in the context of the dark matter problem. Now, the arguments I've given are rather simplistic. We now have much more precise calculations. I'm only going to go through these quickly. I've assumed in my simple analysis that everything is spherically symmetric. And I've got Gaussian fluctuations. None of those assumptions are actually valid. There's a big literature on all of these topics. So let me just very briefly say how you do a more refined calculation. We know, I've told, this is the figure I showed before, pointing out that PBHs are on the Gaussian tail. But in that case, it's actually clear that the primordial reduction is very sensitive to non-Gaussianity because of the high sigma tail. So the assumption of Gaussianity is simply not valid, especially since we're on this exponential tail. And there's been a lot of work on the consequences of the non-Gaussianity. I refer to a paper by Burns there, but leave it at that. The problem of the fact that you may have non-spherical collapse, there's been a lot of work on that as well, and it changes the analysis somewhat. There's no time to go into this in detail, but I just want to point out that when you put in non-sphericity, it broadens the spectrum considerably expected for the mass function of the black holes. Now, let's now get on to the issue, though, of the dark matter. I've told you how primordial black holes may form, but can they make up the dark mass? Well, in a way, this subject goes back to the searches for microlensing way back in the 90s. And you may recall that when they first started looking for microlensing, that's to say lensing of stars in the Large Magellanic Clouds due to halo objects in our own galaxy, the first results suggested that the dark mass was 0.5 solar mass objects. And these were, that was very exciting because primordial...
Let's go back to the last thing.
The last slide? You don't mean the last slide?
I mean this point about the elliptical collapse.
Yep.
So the problem with this is that what we're dealing with is an extreme rare event tail.
Yep.
And what that means is that the entities that are going to collapse will have all sorts of constructive interferences, which will, unless they've figured out something that I don't think would be true, they've somehow got a distribution of that aorticity, and that won't be correct.
Well, it is true that if you're on the high tail, high delta tail, you're more likely to be spherically symmetric, actually. That's something by a lot. Now, this is not my work. This is their work. And I think they put in this, they put it in by hand, I think. So you're asking whether this is reasonable if it's non, I think they treat the non-Gaussianity and the non-sphericity.
They really used our ellipsoid model, right? And
yeah.
the trouble is the values of E are infinitesimal if you're on the extreme tail, because you required, in order to have a coherence, all of the waves having this constructive interference, which is a very rare event. And here, to make this work, you're dealing with the extreme tail. Anyway, so I would say there's probably a big cross here, and you'd go much closer to the spherically symmetric center.
Well, I mean, I'm not going to defend their argument. I think you're right. I mean, it could be very simplistic to assume this is true, because they basically separate the sphericity problem from the Gaussian problem. And what you're saying is that the non-Gaussianity is high Gaussian tail.
What they used was formulas that were based upon Gaussian random tail statistics.
Yeah.
So if they had done their work a little bit more diligently, they would have immediately recognized that it can't be.
Well, they were inspired by normal studies of galaxy formation to do this. You know? Yeah.
It's not a bad case.
I think that's a good point. But let me carry on anyway with the dark mass story, the microlensing story. So the point was, when they discovered this, it was really quite exciting, because we thought, well, what can be half a solar mass? It can't be a white dwarf. We would have seen it. So it could only be a primordial black hole, which would have formed in the naturally form at the quark-hadron phase transition. So this was another exciting moment where we thought, oh, all my life's work is justified. Okay, but unfortunately.
Was the optical depth to these objects high enough that they would actually?
Yeah, that's what goes into the calculation. It's about 10 to the minus 6 or something. But the point is, it went away. So don't get too excited. Okay, the effect went away. And so now we know that the fraction of the universe in these objects is at most, of the dark mass, is at most 20%. And now we've got all these, this is a constraint from a diagram which is quite old now. The halo fraction as a function of mass from the microlensing searches. And you can see that basically you are essentially constraining the optical depth, which is what you asked about. And you can see you're basically excluding the dark mass in a wide range, including 0.5. So unfortunately, yet again, the moment of glory had gone away. But nevertheless, that lensing has been an incredibly powerful tool for constraining these dark objects, in particular primordial black holes. I'll just go through this very rapidly. We've got lensing constraints over, this is the mass range here, and this is the fraction of the halo, just to give you some idea. So, for example, the microlensing, the macho microlensing constraints are excluding this region. Femtolensing of gamma ray bursts is excluding, rather remarkably, a tiny mass range. This is actually gamma ray bursts and femtolensing. That's way over there. There's the microlensing of quasars, which is excluding this region, and there's the millilensing of compact radio sources, which excludes that region. So the point is, lensing is an incredibly powerful tool over a huge range of mass scales. This is the Bernanke cell constraint from gamma ray femtolensing of from 10 to the 17. That should be a little g, I guess. 10 to the 17 gram black holes. Then there are the dynamical constraints. Now again, we have a whole long paper on this. Let me just summarize what they are briefly. There are the dynamical constraints shown in green. You disrupt binaries if you're above about 500 solar masses. You disrupt globular clusters. You tidally disrupt globular clusters above about 10 to the 4th solar masses. You overheat the disk above about 1 million solar masses, and dynamical friction brings them all into the center of the galaxy if you're below about, again, 10 to the 5th solar masses. So there are a huge range of dynamical effects, which basically are this green region, which are putting constraints. There's also accretion effects. Big black holes will accrete and distort the spectrum or make anisotropies in the microwave background. So there's been a lot of interest in that. But basically, all the constraints are summarized in the paper I did with the Japanese in 2010. So all these regions here are basically constrained. So this is constraint on the fraction of the dark mass in black holes as a function of mass.
How significant is the accretion constraint? Because we have a black hole at the center.
Well, I mean, look, between you and me, I never take those too seriously because there's so many extra parameters that come into this accretion and constraint. I mean, accretion efficiency, it assumes Bondi accretion, and so, you know, any of these conditions, any of these constraints you can have a little argument about, but I've never been too worried by this. But there's no doubt in principle accretion is going to give you a constraint, but how much you scale this by, you know, astrophysical parameters is another matter. But let me then just summarize the situation. This was the situation, that's really about 5 years ago. There seemed to be, this was excluded by femtolensing, this range was excluded by microlensing, and above 1,000 solar masses was excluded dynamically. So there seemed to be 3 little windows where the dark mass could exist. There was a little window between about 10 to the 16 and 10 to the 17 grams. I call those atomic PBHs because that's what their size is, not their mass. There was the sublunar mass range, and there was the intermediate mass range, which I guess is the most interesting at the moment. So those were the ranges which we had originally. And in principle, there was still also the possibility of the Planck mass relics. So remember I talked earlier about how a black hole may stop evaporating when it gets down to the Planck mass in answer to your question. And so those would be natural. That would be a very natural way of making the dark mass. Since then, there have been all sorts of constraints on these 3 windows. And I don't have time to discuss them in great detail. I'm just going to show up the papers so at least you know. I want to give some impression of what sort of constraints there are. In regards to the constraints on this sublunar range, the lunar range, a lot of people have argued that if you have dark matter in that range, this is in grams, the black holes are going to get captured by white dwarfs and neutron stars. They'll destroy the white dwarfs and neutron stars, and that leads to various constraints. This is the dark mass fraction as a function of mass. You see lots of diagrams like this in the literature. And indeed, Panny and Loeb argued that this definitely killed the scenario. That paper was definitely wrong, but anyway. People have argued that some of these black holes may go into white dwarfs and actually trigger the white dwarf to supernova. So this is another constraint which has come out recently. Looking now at the intermediate mass black holes, you may recall that one of the key upper limits there was the disruption of binaries. And the constraint I gave before was about 400 solar masses. That's to say you can't make the dark mass bigger than 400 solar masses, else it disrupts binaries. But more recently, people have looked at this in more detail and argued that that mass of 400 solar masses could be much smaller. So there's no time to read all this, but just note the author if you're interested. The lensing of fast radio bursts could be an important probe. And I was talking to Sherry yesterday, and she was involved in CHIME. And CHIME, because we're involved in CHIME here, is that right, Dick? CHIME is going to be an interesting probe of these fast radio bursts, so that would be a way of looking at it. Brandt has pointed out that you get strong constraints on the intermediate mass scenario, because there's a particular dwarf galaxy called Eridanus II and a star cluster which has not been disrupted, and it's only one object, but he builds up a huge set of constraints based on that, which is this red diagram. So in the paper with Kuhnel and Sandstedt, we put all these constraints together. So this is, if you like, is an update of the figure I showed you with the Japanese. And this is basically the most up-to-date constraint, all color-coded. And it's always updating. We keep getting letters saying you haven't put our constraint in, so that probably won't be the final version. But again, what you can see is it confirms that you've really now only got 4 windows. There's the intermediate mass window, the sublunar window again, and there's the atomic window, and then there's the Planck mass relic, which is sort of goes off the diagram. So those are still the diagrams. And what the point in our paper, and of course this is interesting if you want LIGO to detect them. Never mind this. I'm just going to finish. So what we've done is we go through these 4 windows in great detail, looking at all the constraints from lensing and dynamical and wide binaries. That's scenario A. This is scenario B, where all the neutrons are, and this is Kepler microlensing coming in. This is scenario C, which remember is the just 10 to the 16 to 10 to the 17, where femtolensing and the extragalactic gamma rays. And this is the Planck mass relic constraint. That these are removed by inflation, and these, the black holes, the relics dominate at evaporation. So we've gone through that in quite a lot of detail. But in ending, I want to say there's one really important point in our paper, and that's the following. Most of all the constraints I've shown you assume that the mass function is monotonic. It assumes that all the mass is at a particular scale. But what happens if you have an extended mass function, which is what is actually likely to happen? All the realistic scenarios, the PBHs are not going to have a single mass, they're going to have a mass function. And that is good news and bad news. It's a two-edged sword. First of all, it means that the PBHs may still be provide the dark mass, even if the fraction is low at any particular scale. I mean, if my dark mass fraction is 10%, if it extends over a decade of mass, I can still make the dark mass. On the other hand, it could be bad news because the dark mass, it may be that if I want the dark mass to be at a particular scale, then I'm going to violate the constraints at some lower or higher scale. So it really is quite important. And this was just showing you why you expect to get an extended mass function. I told you about critical collapse, you remember earlier on, that if critical collapse is what occurs, then you have an extended mass function. This is non-Gaussianity, which has the effect of extending the mass function. This is for 2 particular scenarios. It's an axion curvature inflationary scenario and a running mass scenario. But it's just showing how the predicted fraction actually is very spread out. So the idea that you have to have all the dark matter at a particular mass is very naive. Now, here is the non-sphericity argument, which Dick says may also be very naive, but it doesn't matter. The general point I'm making is that you expect, in all scenarios, you expect an extended spectrum. Never mind that. This is when you have a phase transition where you get an extended spectrum. But that's the general point I'm making. The important point of that paper is that when asking whether the primordial black holes make up the dark mass, you do have to allow for the fact that they may have an extended spectrum. And I don't think anyone's ever really done that properly before. So I'm bang on time, except it's I've gone to the full hour. But let me give my conclusions. PBHs are a unique probe of the early universe and the various cosmological parameters associated with their formation mechanism, which I talked about at the beginning. There are 4 mass windows where they could comprise a significant fraction of dark mass. The intermediate mass one is the most topical because of LIGO. It's my favorite. The other windows, between you and me, the other windows are so narrow, they're rather implausible. This at least is quite a broad one. And so, of course, and I've tried to give some idea of how we can actually probe this. If this is the dark mass, we'll find it. We'll find it through LIGO. Well, that depends on how many are in binaries. We'll find it through CHIME. There are all sorts of constraints, ways in which we might in principle know this is the case. I have to say, I really still rather love the Planck mass relics because I think it's not implausible you have Planck mass relics. And I like the idea that all the dark masses in these, 10 to the minus 5 grain of sand type dark mass. But, of course, as I said in my abstract before I hid it, the problem is that Planck mass relics, the smallest conceivable objects in the universe, 10 to the minus 33 centimeters, I don't know any way you're ever going to detect them except through their gravitational influence. So that's why I said that they would be virtually undetectable. So right now, my favorite candidate are the intermediate mass black holes, because, of course, they are detectable. And then the other point is, of course, as I stressed in the last part of my talk, an extended mass spectrum is expected, and therefore special care is required when comparing to the constraints. And in doing that, a detailed understanding of PBH formation, allowing for non-Gaussianity, non-sphericity, etc., is crucial. So thank you.
All right, well, I need to run, and you're past time, but I think we should please take a few questions. So, ready?
Maybe, given all the range of constraints you showed many papers that would, one which intrigued me is the Tim Bond, who is a faculty here, has you clearly had a plot where you shaded his constraint region to be less restrictive. Why?
Sorry, we cannot. Oh, I have to be very careful. Let me go back a bit. Who are we talking about? Sorry.
Okay, when you showed, I think, one of the constraints where you overlaid all the, combined all the known area on the next one.
Yeah, you mean the diagram here? That one there?
On the next one, a bit further down, then you showed how various recent papers
Yep.
close window A, so you got the box point E, and then you go down.
Yeah. Oh, sorry. You mean this one here? Yeah. This.
Exactly. So
Yeah.
the top left scenario A,
Yeah.
you're willing to shrink this constraint window.
Well, the point is, this constraint is coming from Eradinus, okay? Eradinus, sorry, is the author of that paper here? Is that what you're saying?
Not in the room, but he's
Oh, he's not in the room. Well, I mean, I wouldn't mind. I mean, this is a very important constraint, but the skepticism I expressed was only related to the fact that it's one object, okay? It's one single dwarf galaxy, and you're looking at one star cluster in the middle of it. And I would not be, you don't know whether it's atypical. But the point about this, I mean, if he is in the room, this is a great tribute, because we thought this limit was really important. And we use this to exemplify the methodology of how you considered a mass function. Let me show you how this works. For example, these different dotted lines correspond to different models for the density of the dark mass. But you see, if you believe this, then the constraint hits the microlensing constraint at about 0.4. Now, 0.4, you might say, can that be the dark mass? Well, in principle, you could have 0.4 above and 0.4 below. Okay, so you could have 0.8. So if you believe that form of the constraint, you couldn't make the dark mass. However, if we take this form of the constraint, which corresponds to a different dark matter density, it's 0.5. And 0.5 would allow you just about to do it. I mean, obviously it's taking fine-tuning, but it's 0.5 above and 0.5 below. And if it was this curve, 0.8, you could easily make up the dark mass. So you see, if you look at this diagram, naively, you just say, I can't have F equals 1, therefore the primordial black holes can't be the dark mass. But the point we're making is that you can still make the dark mass even if F is less than 1. But you just have to look at it rather carefully. So, so I'm very grateful. I know he's not in the room, but I thank him very much, because that was very useful for our paper. Yes?
I have two questions to the relation to LIGO.
Yeah.
One corresponds to the same plots you have on this plot, and this is your mass fraction F.
Yeah.
How easy is it to relate F to actually a coalescence rate of the planet?
Well, pretty difficult, because the point is, F is the fraction of the universe that went into these primordial black holes. But of course, in order to have coalescences, you've got to have them forming binaries, and that's some fraction which you can't easily calculate. And then you've also got to have some, they've got to be at the separation such that they coalesce at the present epoch. So that's another fraction. I mean, when Dick and myself wrote our paper, we went through the same analysis, trying to work out what that fraction was. I mean, let me just say, oh, it's too far to go back, but do you remember I showed the paper by Sasaki et al., where they're calculating the PBH coalescence rate. So that's an attempt to calculate, to do that calculation more precisely. So you can do it, but there's a huge amount of guesswork involved. Because, as I say, we just don't know what, as I said before in answer to your question, these black holes are going to capture each other later on. They're not going to form in binaries. The thing about population 3 stars or ordinary stars is they're likely to form in binaries, okay? And then it's just a question what fraction are at the right separation, and that's something we can answer because we have observational evidence about the separation of binaries. For primordial black holes, you just have to have a model. So the real answer is that we can't predict the coalescence rate because of that uncertainty. But it's still true in principle. People have tried to predict it, and in principle, it could be the case. So, I mean, I think the big question is how can you tell whether the LIGO events are primordial black holes or ordinary black holes? As I said, when they formed is more or less irrelevant. And I suppose the question, you'll get your clues from the eccentricity of the orbits and things like that, because you'll have different models depending on how they're captured. If a black hole forms in a binary, if the binary forms, if it formed as a binary, you're going to have a different distribution than if it was actually formed by capture later on. So I think those are the sort of, people have thought about that. And then, of course, there are indirect arguments like Kashlinski's argument that if you had the primordial black holes, they would do other things as well. But I do think it's just interesting that the LIGO mass range is just in the window which is allowed.
Especially if you look at your top left panel,
Yep.
the 30 solar masses is right where the constraints are weakest.
Exactly. I mean, in this diagram here, 30 solar masses is just about where it comes.
So the x-axis of the scale from 1 to 1,000 is pretty exactly the mass range LIGO is searching for.
Yeah, I guess that's right.
There's always this big question to how low masses to search.
Yeah.
Currently, 1 plus 1 solar masses is the upper limit. There's big incentives going higher, say 1.2 plus 1.2 solar masses, because it makes the searches computationally tremendously cheaper. Conversely, we could go lower, say to 0.5 plus 0.5 solar masses, but this would make the searches exceptionally more expensive from the computing side. Is there any reason from this primordial black hole picture to put effort into this 0.5 to 1.2?
Independent of whether they're primordial black holes, I mean, these lensing limits are, this is why and there are many other lensing limits besides Eros, by the way. I mean, they're listed in our paper. There are lots of lensing constraints, and it's the lensing constraints which tell you can't have the dark mass, or you can't have much dark mass at this lower mass end. But of course, LIGO doesn't need the dark mass to be in these objects, because you don't need a critical density, the 0.25 critical density of these objects to make the LIGO burst. So I mean, it's just. I would say though that this is a constraint. Although I've been talking about this as a constraint on primordial black holes, it's a constraint on any dark matter candidate, any black holes as well. So. You should be aware of that to see whether that is. It's an interesting question whether you actually, this means it's not worth looking with LIGO, because even if it's only 10% of the critical density, it doesn't mean LIGO can't detect them.
Well, it depends how efficiently they are made. Because
Yeah.
LIGO has a range of about 100 megaparsecs or so.
Yeah.
And even if it's 10 to the minus 10 of the critical density, you still have zillions of them within 100 megaparsecs.
And it's important because, of course, we know normal black holes can't form below about 10 solar masses. There's no evidence for any black holes below 10 solar. So what you're saying is that if you LIGO found black holes below 10 solar masses, they would have to be primordial. That's what you're saying.
Well, first of all, LIGO is searching for binary compact objects. It's very difficult to distinguish black holes from neutron stars.
Oh, sorry. Yes, of course. Yeah. But I mean, but nevertheless, according to the norm, I think I'm right in saying that there is a mass gap, that there's no evidence for any black holes below about, is it 10 or whatever? It says, sorry? 5 to 7. So 7 solar masses. So in some sense, we would be surprised to find any black holes less than, say, 7 solar masses.
You would also have been surprised to find only 30 solar mass black holes.
Yeah.
That's the beauty with new experiments.
Yeah. But that's an interesting question, though, because one can ask whether the microlensing constraints and these other constraints actually already exclude objects in that range below 6 solar masses. I've not thought of it in that way. That's very interesting.
Discussion seems like it's switched over to coffee and tea mode. So, barring any other quick burning questions, maybe we can thank Bernard.